our second presenter for today, Dr. Ellen Lee. Welcome, Dr. Lee.
Thanks, Elizabeth. Shawn very kindly walked us through some of what goes on in terms of biophysical characterization and how that affects biologics. What I hope to discuss in the second portion of our chat today is just to kind of give you an idea of some of the other types of measurements, other kind of applications that is possible with the GCI technology that Shawn utilized in sort of his trastuzumab measurements. So when we think about looking at measurements, trying to decide what's an important molecule, be it small or biologic to develop, we think about measurements of affinity, but there's also the consideration of kinetics. As we think about something moving through the process from hits to leads to hopefully a final drug, as we think about affinity versus kinetics, as we think about the development of a drug processes, affinity is a really good place to start, but kinetics also comes into play because we can think about affinities is that ratio of both K on and K off, and you can have multiple drugs, multiple candidates with the same affinity, but it is quite possible for them to have different kinetics, and that's sort of illustrated for us here on the right-hand side, and it's with simulated data. I just always find it a little easier to think about things visually, and when we look at that right-hand side, we do see that they have quite different kinetics, even though all three in purple, green, and teal blue have essentially the same affinities. Today in particular, I'll just be presenting a bit on the Creoptix wave system. And to fit with today's sort of discussion, we'll be discussing sort of more case application samples to do with sample robustness and the types of samples and matrices that the instrument can help you evaluate projects in. But to start with, we should always discuss a little bit about what's the underpinnings of the technology. And in this case, I find it useful to discuss sort of how we're able to have sensitive measurements by discussing the waveguide interferometry to begin with. For a lot of people, it's useful to think about this in comparison to surface plasma resonance or SPR, since a lot of biophysicists are very familiar with the technique. SPR works by having a light shown on the back of a thin gold surface, and we are looking at that total reflection angle. Part of that light generates an evanescent wave, or the plasma on the top side of the gold where the sample is. In this case of the cartoon on the left-hand side, we're looking at an antibody antigen with the antibody mobilized to the surface. This means that when we're looking at the spectrum of the reflective light, there is going to be a negative peak, a dip at a certain wavelength. The plasma on the top side is going to be sensitive to the refractive index of what's above that surface. With that proper referencing, the refractive index changes can be converted to mass bound on a surface. When we have a refractive index change, for example, antibody binds to its antigen, we have a change that we can then detect. When we are talking about waveguide interferometry, which is going to be illustrated on the right-hand side of the slide, it is going to be similar. There is an evanescent wave that's generated by light and sensitive to the refractive index on the surface. Therefore, we can also use this to measure mass differences. One of the major differences I really like about this cartoon, which I think is nicely illustrated here, is that with waveguide interferometry, the light is traveling inside a waveguide and under the sensor surface. I think about it kind of like a optic fiber situation. Because of this, the evanescent wave here kind of travels along that surface and isn't static. This means that, practically speaking, with waveguide interferometry, the waves feel a lot more of interactions on that surface than SPR plasma. It's part of what makes waveguide interferometry more sensitive than SPR. However, classic waveguide interferometers do suffer from some stability issues. And here at Creoptix, we've sort of figured out our way around it so that we can take advantage of the sensitivity. So with Creoptix grating-coupled interferometry technology, what we've done is to take the light that's utilized in waveguide interferometry, and we couple the light in through the grating. So now, rather than having two different light paths that would eventually cross in old interferometers, which was due to drifts from vibration temperature changes, by having them travel in the same waveguide, we remove the possibilities, remove the causes for any data drift. So that's why this technology is GCI, short for Grating-Coupled Interferometry. We've taken the waveguide interferometry, we've made the data readouts much more stable, giving us the ability to access that higher stability possible.